significant transformation from world scale simulations to atomistic scale simulations. And today I will try to give you a flavor what kind of applications we perform in these HPC systems. And I will give two examples, one quantum particle simulations for materials, and the other one is the development of machine learning potentials for particle materials simulations again. Sorry. And, okay, let me warm up a little bit and the story of my career. And this is the computer, AI-generated computer I used for Master of Science studies. It was based on Pentium 4 CPU, and the memory less than 1 GB. Then we upgraded our system for computational purposes. It was the homemade cluster. We connected desktop computers with gigabit Ethernet, and again, memory per node was less than 1 GB, and the computer was based on Pentium 4 CPUs. And then we found project support. We upgraded to a professional system. It was Sun, and it was based on Blade servers, and AMD Opteron was new, and dual core, 8 GB. It was amazing computer for my PhD studies. Then, and in the mid of my careers, I built another, design and built another cluster. It was amazing, and 15 nodes, Xenon-based CPUs, and 64 GB memory per node. It was really good. Then I used professional systems, HPC clusters, but the story is like that. And now we drive very, very good, very sport cars, if you consider the current HPC systems. But I don't know, this is the nature of human. It is not enough. It was always not enough, and it is still not enough. Okay, and we use different kind of systems during my career. The improvement is significant. We have many different clusters all around the world, hopefully open to everybody. And we use these systems to simulate materials. For my career, my main concentrate was on simulation novel materials for energy harvesting applications, like piezoelectric, ferroelectric, solar energy type of things. And yeah, I did several works on those, always using the available cluster systems. We mainly solve many particle Hamiltonian, which includes different quantum interactions. It is a very complicated problem. Depending on your target, you have to use different approximations. Depends on the level of approximation, the complexity is different. The required HPC power is different, and we always target different systems to solve these kind of problems. Today I will give two examples. We mainly performed in available clusters around Belgium. And first one is the many-body quantum simulations for excitons, and the other one is the machine learning development of machine learning potentials for different material systems. And let's start with excitons. And actually, I try to keep it basic to make clear for broad audience. And you are familiar with atoms, I am sure, everybody. And this is AI-generated picture of atom. We have core and electrons around. It is simple here, but in quantum world, it is highly complicated. And these atoms get together in a particular symmetric structures and makes materials. Like here we see the left from the left. First one is silicon, which is significantly used in chip industry, semiconductor industry. Everybody has silicon in their pocket now, and diamond and gold and copper. We have different materials with different arrangement of different elements. And then this is the very basic picture of the electrons in these elements. This is for semiconductor. For example, in silicon, electrons arrange in this way. And this is the quantum picture, because therefore we have discrete energy levels. In quantum level, we don't have continuous energies. And we can disturb this ground state by simply using light. We can excite one of the electron to higher energy levels. And if we remove light, we will go back to, again, the ground state picture. But in quantum world, which is not that simple, because after we remove light, you see here, after we apply light, electrons arrange themselves, at the ground state electrons, arrange themselves in another way, simply. Then we have intermediate state. Before placing to the ground state, these higher energy electrons occupy an intermediate state. We call it exciton. Normally, most of the materials, the lifetime of this metastable state is very low. But now we have novel materials, the lifetime of these metastable states within the usable range in future quantum applications. And these excitons are very important for future technology. Hopefully, we can model these electrons in a simple picture, and we simulate excited electron as an electron, and the rest as a whole. And it's a kind of interaction of harmonic state of opposite particles. Okay, and here, this is the definition of the electron, the metastable state of particles in materials. In order to understand the physical features of these particles, we perform three-step simulations, quantum mechanically. First one is very quick and easy in HPC computers, but the other two steps are highly complicated, depend on the material, and depend on your target. And near future, actually, recently, these particles has been investigated by many different groups around the world, experimentally, and we calculated quite interesting properties for these particles. We investigated how we can possibly use those particles in technological applications. But we still have problems. The last one, before we solve, was that. Actually, let me use pointer, sorry. This is the picture of excitons. The experiment is basic. You place a material and you measure the light-matter interaction, and you identify the energy of different excitons in this material. But at the same time, you apply a field along the out-of-plane direction of this material, and you manipulate the energy of these excitons. It's not, here. And here, as you can see, you manipulate the energy of these different excitons. Normally, for electrons, we expect linear change, as you can see here. And it should be linear around this 0, and it should be symmetric. But excitons, it is different, because here we have some nonlinear behaviors. Here it is obvious. We have linear. At some point, it becomes nonlinear. And it has been speculated many different ways, but nobody addressed this change with exact quantum mechanical level simulations. Then also, the other point was, for some materials, it is symmetric, as you see previously, but for other materials, it is not symmetric, as you can see here. It is not symmetric around zero field. Again, different experimental groups have speculated the reason, but it was not clear. Then we performed simulations, quantum mechanical level simulations for these particles, and in ideal case, you can solve this problem with 22 different cases. For 22 different cases, you have to perform different level simulations. In general, it takes 3 million simulation time in available clusters, CPU time. But this is the ideal case. In order to solve this kind of problem, you have to invest more than that to make your simulation reliable. Then, eventually, we end up with the results. As you can see here, we identified different excitons in materials. We have constant changes, as you can see here, with a slight white line. And we have almost linear lines, as you can see here. And also, we have other excitons change with energy. Here you can see quadratic nonlinear behaviors. And basically, we cleared out why we have this behavior for different excitons. I will not give technical details. If you want to discuss later, we can discuss the reason. And also, we predicted that the non-symmetric behavior around zero field is totally due to the geometric effects or structural properties of the materials. Then, because of that, in some experiments, we have symmetric change with field. In some other experiments, we have non-symmetric change with field. And hopefully, we published our results, and we believe that it became a kind of good contribution to the literature. And we also performed different simulations for different properties of these interesting particles on both VSC and LUMI clusters, and published recently. This was the story about the excitons, these interesting quantum particles, and this part is related with the development of machine learning potentials. In atomistic simulations, we want to basically, in our research group, we want to understand the dynamic behavior of materials, time evolution of systems. And in order to understand the time evolution systems, one of the best way is molecular dynamic simulations, we call it. In molecular dynamic simulations, we follow the position of each atom in the system in time frame. In order to do that, we need the correct definition of interaction between atoms. We call it potential field or force field. And machine learning is it seems that is very good technique in order to build these kind of potential fields to perform molecular dynamic simulations. I will show you some examples. Okay, this is the example for quantum particles. These are the particles, for example, this one built with 60 atoms. Those are built with 150 atoms. Very small particles. It is used in different applications like catalysis or drug design or even in cancer cure. And understanding the light-matter interaction, again, in this particle is very important. And understanding their geometrical structure in different temperatures is also important. And our idea is based on, actually, it is not solely our idea. It is a kind of common field now. Many different research groups try to develop a kind of potential like here. Basically, in this level, quantum mechanical simulations, which are very accurate, is possible. But in this level, it is not possible. The idea is very basic. Perform quantum mechanical level accurate simulations for these small particles, build a machine learning potential, and solve large particles. Then, if your potential works well, there is no limit about the number of particles. To do that, you should first generate data. This is the energy spectrum of different particles. You should first generate data. You should select particles, different particles from your energy space, and train a machine learning potential. Then use it for large particle time evolution simulations. That is the idea behind it. And hopefully, this works pretty impressive. And for example, this is the classical technique we use to calculate the energy of the atomistic nanoparticles. And for larger particles, you see the difference between the energy and the difference between the energy calculated with very accurate method and the classical technique is very high. Out of the range, we expect for an accurate simulation. But for machine learning, it is pretty impressive. Okay, then as I said, currently we still work on this problem. Currently, we can generate accurate potential in order to understand the dynamics of materials. This is the application for melting. For example, we start simulating a large particle. We increase temperature little by little. We increase, and we see here a melting point. And therefore, we can understand the effect, the melting nature of these large nanoparticles with different shapes. And we can address more stable, for particular application, we can predict more stable nanoparticles for particular applications. Sorry. And this is another example. As I said, this nanoparticle level simulation still going on. And this is another example that we use our machine learning potential in order to understand the thermal conductivity of particles or two-dimensional materials. And here, these are the calculations reported in the literature. You see, the deviation is significant. And different techniques result in different thermal conductivity values. In order to address this deviation, we developed a machine learning potential, and we calculated the thermal conductivity with different techniques. And also, we address why these calculations are different from each other. And finally, by using these machine learning potentials, we obtained very good results, very good agreement with quantum mechanical based simulations. And this then we compare with these simulations, these results, with different techniques, and also with different potentials available in the literature. Nowadays, there are some foundational models you can directly download and use to simulate your structures. We compare with them as well, and our results shows that current machine learning potential developments are very good enough to define the thermal conductivity in low-dimensional materials level. And we revise our results in this paper. It will be published soon. In a week, I think it will be available online. And you can, if you are interested, you can read and see how these different type of potential definitions will result in thermal conductivity for different materials. Okay, these are the examples that we actually that show our general interest and our general activity on different systems. For these kind of simulations, we mainly use the VSC resources, Leonardo and LUMI. And for the quantum simulations, for exciton simulations, we use Yambo. And we personally build it. I am sure it is not efficient and it is not optimized well, but we just follow the instruction without error, then we use it, and we do not try to optimize it, because when we do it, we screw up. If you help us, and maybe we can do it better. And for the machine learning, we basically use CPU and GPU available in Gantt cluster, tier 2, and we perform all the training activities there. And VSC people help us very much, especially Bert, about installations. And I think we will have a better approach soon. And on Leonardo, actually, for Yambo, in exciton level, the computational cost is different for different materials. For example, actually, they named for the materials named semiconductor, it's couple of days in couple of CPU nodes. But for metallic structures, it is couple of days in at least 20 GPU nodes. And this is different. We use both successfully, Yambo, which is installed on Leonardo by Yambo team, and which is located Modena, Italy. And they did very good job. But to calculate, there are some limitations. For we also use LUMI. In CPU, it runs very well without any problem. But on GPU, unfortunately, we are not successful. We couldn't solve many problems. We are looking for support, if it is possible. But some part of Yambo still works. If it works, it is very fast and accurate. But we have to solve some problems. Okay. I want to mention another point. And nowadays, in computational science, project success rates are very competitive. We are dealing with maximum 70% of success rate. We have to submit always, we have to submit many different proposals. And to use especially the European level computers, again, we have to submit full proposals in every year, which is a kind of stress for us. Maybe for the extension of the current project, another model could be used, and it will help very much to us. And so this is the story, and we use these HPG systems for material simulations. And during my career, I always use these systems, and I build my success on these computers. Therefore, thank you very much for your support and help.